Okay, welcome to this YouTube channel. We are still on Best Science Brain YouTube, displayed here. Then our Facebook page, Best Science Brain also. We'll have an experiment on spiral spring involving simple harmonic motion. We'll have the setup, have the spring. We'll have the mass hanger. We'll have slotted masses. We'll have meter rule for taking measurement. Then we're told you have been provided with a rotor stand, clamp and bus, set of masses, stopwatch, split cork, and other necessary apparatus. Using the diagram above as a guide, carry the following instruction. Number 1, suspend the given spiral spring vertically as shown in the diagram. Number 2, suspend a mass hanger on the free end of the spiral spring and add a mass of 50 grams on the mass hanger. So after the suspension of the spiral spring, we're going to add a mass of 50 grams on the mass hanger. Then pull the hanger gently downwards and release it to set into vertical oscillation. Determine the time T for 20 complete oscillations. Evaluate the period. Period is the time of oscillation over 20, that is the period. And also evaluate the sphere of period. Number 4, repeat the procedure with mass 70, 90, 130 respectively. In each case, determine the time T and evaluate period and period sphere, tabulate the readings. Then plot a graph of T sphere on the vertical axis and M on the horizontal axis, starting both axes from 0, 0. So the summary of the experiment is we're going to hang 50 gram mass and set it into 20 vertical oscillation, record our time, and find the period. After that, we'll repeat it using 70 gram. After 70, we use 90 gram, 110 gram, and 130 gram. In each of them, we set each mass into 20 vertical oscillations. Take our time with the stopwatch and find the period. Period is time over the number of oscillations. So we'll go to the experiment. So what we're holding is the mass hanger. The mass hanger of 50 gram. So we're going to slot the first mass we're going to oscillate is the mass of 50 gram on it. We'll hang it on the spiral spring. So we're about to set this into 20 vertical oscillations. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What time do you have? 22.98. 22 point what? 98. We have 22.98 for the 50 gram mass. So repeat this. Repeat it to have another reading and then take the average. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 22.57. So we'll find the average 22.98 over plus 22.57 divided by 2. Okay, we made a mistake here. This place should be T1. This place is what? T2. So there's no need for this column. So what the average? 22.76. 22.76. Yeah. Okay. So let's divide by 20. Let's get our period first.
1.139.
1.139. So find the square of the period.
1.297.
1 point what?
297.
297. Okay, let's continue. This is serial number 1, 2, 3, 4, 5. So we'll go to the next mass, that is 70-gram mass. So we'll go back to the experiment. This is 50-gram mass. We'll slot in another extra 20, making it 70-gram. We're going to take this 70-gram into 20 vertical oscillations. Please return your time to 0. Have you? Okay, well now let's wait. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What do you have there?
22.74.
22.74 as our first time for the 70-gram mass. Okay, so let's repeat the process again for the 70-gram mass. The 20 oscillations. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So for the second time interval, we'll have around 23.10. So add 22.74 plus 23.10 and divide by 2. 22.92. Then find the period, divide it by 20. Period is time over 20. Since we did 20 oscillations, divide 22.92 by 20.
1.146.
1.146. Square 1.146.
1.313.
313. So we'll now move to the next mass, 90-gram mass. 90-gram mass. This is already 70. We'll slot in extra 20, giving us 90 gram. So we'll subject this to 20 vertical oscillation. First of all, let the spring be still. Then we can now oscillate gently. No, it's not getting right. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 20. Have 20. What do you have there?
25.46.
25.46. So that will have for the first experiment. You repeat it to avoid random error. So you go ahead. Start. We have this. We're going to set it the 90-gram mass again. Repeat the experiment. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So what time do you have there?
26.72.
26.72. So find the average, 25.46 plus 26.72 divided by 2.
26.09.
26.09. So divided by 20, let's have the period.
1.305.
1.305. Then square it.
1.702.
1.702. So we see we are in order. The period is increasing. So we'll now go to the next one, 110 gram mass. Already on the spring we have 90 gram. So add extra 20 to make it 110. We'll now return your stopwatch to 0. So we're going to oscillate 20. We're going to oscillate 20 oscillations from the question, the instruction given to us. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What time do you have? 34. That's big. 34 point what?
83.
Let me check very well. 4.83 seconds. So we're going to repeat this experiment again and take the average. Return to 0. No. Not vibrating well. Not oscillating very well. Okay, 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What do you have there?
36.76.
36.76. So add 34.83 to 36.76. 34.83, 36.76, and divide by 2.
35.79.
35.79 divided by 20 to find the period.
1.789.
789, 1.790. Then square 1.790.
3.204.
3.204. That's the Y value. Okay. Now move to the final mass, which is 130 gram mass. So go back to the spring. What we have here is already 110. We'll add extra 20 to make it 130 gram mass. Okay. So return your watch to 0. The mass is heavy, as you can see. So we're now going to move and oscillate. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What do you have there?
37.19.
37.19. So repeat the process again and take the average time. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. What do you have?
That's 8.05.
That's 8.05. So add and find the average. That's 7.19 plus that 8.05 divided by 2.
37.62.
That is 7 point what?
62.
Divided by 20, then get the period.
1.881.
881. Square it. 1.881 squared.
3.538.
5 what?
38.
So you see that our results are in order. The period is increasing as the mass is increasing. The mass are increasing. While the period is square. So let's go to the system and compile our results and then do the graphing. So we have our table which we got from the experiment, which we just did 2 minutes ago now. So we'll go to the system and then look at the same readings on the system now. Surround the system, how the mass of hanger 50.00 gram. The first mass hanging is 50.0 gram on the mass hanger, set into 20 vertical oscillation, will obtain time of 22.98 seconds. Repeated, will obtain 22.57 seconds. Then the average time, the mean time, adding T1 and T2 and divided by 2, will have 22.76. Oh, there's a mistake somewhere. Yeah, there's no mistake. So our T1 to 2.98 seconds, T2 to 2.5 seconds, that is repeating it. Then the average time, which is T1 plus T2, giving us 22.76 seconds. So the average time is obtained by adding T1 and T2 and dividing by 2. That is T1 plus T2 over 2, as we can see on the screen, on this column. So to get the average time for the 50 gram mass, we'll have 22.58 plus 22.57 divided by 2, we'll have 22.76. The period is nothing but the time, this average time, over the number of oscillations. We did it for 20 oscillations, so this period is 22.76 over 20, giving us 1.136. So period is capital T. Then capital period square gives us 1.29. If you square 1.139, we'll have 1.297. We'll go to the 70 gram mass. In the first experiment for 20 oscillation, obtain a time of 22.74 seconds. Second oscillation, we repeat it again and obtain time of 23.10 seconds. Then the average time, which is T1 plus T2 divided by 2, as we have there, will give us 22.92. Then our period, which is the mean time over 20, 22.92 over 20 gave us 1.146. Then square of period gives us 1.313. Then going to the 90 gram mass, our first oscillation, 20 oscillation, gave us time of 25.46. Repeated it to avoid error, we'll have 26.72. To the average time, we'll have 26.09. Our period is 26.09 over 20, which is 1.305. Then period squared gives us 1.305 squared, giving us 1.702. Then taking a mass of 110 grams, our first time we did the first oscillation, first oscillation, we obtained a time of 34.83, pretty somehow larger than this one. 34.83. Repeated again, we got 36.76. Then the average time on meter, which is obtained by adding T1 to T2, that is 34.83 plus 36.76 over 2, divided using this formula above, we got at 5.79. Then the period, which is the time over number of oscillations, that is 5.79 over 20 oscillations, gives us 1.790. Then square of period, that is T, capital T square, gives us 3.204. Then the next is mass of 130 gram. We set it into 20 vertical oscillation of 10 time of 37.19 seconds. Repeated, we have 38.05 seconds. The average, we have 37.62. That is adding these two and dividing by 2. We have 37.62. Then the period, which is time over number of oscillation, that is 37.62 over 20. We obtain 1.881. Then square of period square gives us 3.538. So these are data. How do you know you are correct? Your period should be increasing. As the mass increases, your period should also be increasing. Likewise, the square of your period should be increasing. So having done that, the next question. So the next question is question number 5, where we're asked to plot a graph of T square, that is square of period, on the vertical axis and mass on the horizontal axis. So we're going to the graph. So we have our readings on the table displayed here once more. And we are plotting T squared against mass. The highest value on T squared axis is on T squared column is 3.538, while the least value is 1.297. Then mass, the least value there is 50.00, and then 130, the highest value. We are plotting period square, that is capital T squared, on the vertical axis, and then mass on the horizontal axis. So let's go to the graph. So on the graph, we have T's period square, square of period on the vertical axis, and then mass on the horizontal axis. So as we said, the highest value for period is 1.297, that is period squared, and the least value is 1.297, sorry, and the higher value is this value is 1.297, higher value is 3.538. So look at the scale. We chose this is 0.5 here, 1, 1.52, 2.53, 3.54. So we chose one bus or 2 cm represents 0.5 units on the T squared axis. And then on the mass axis, we go to the table again. The highest value for mass is 130, the least value is 50. So let's go to our graph. On the graph, we have 20, 40, 60, 80, 100, 120, 140, covering the range from 50 to 130 for masses. And then we chose the scale here. We use one bus for 20 units. That is 2 cm for 20 units on the S or mass axis. As we usually do, first of all, find out what one tiny line represents. To know what one line represents on the T squared axis, what we'll do is we divide, since the first unit, the first value placed on the T square is 0.5, divide this 0.5 by 10 lines. There are 10 lines in one bus. So 0.5 by 10, we have 0.05 units. So one tiny line on the y-axis is 0.05 units. We'll now move to the m-axis to know what one line represents. One bus represents 20 gram mass. So for one line, we divide this 20 by 10 lines. We now have 20 over 10. That gives us 2 units. We now plotted the graph. We obtained a straight line graph starting from the origin. A straight line graph, and from the graph, about 3 points on the graph. 1, 2, and the third one there, 3 points, and why 2 points out of the graph due to experimental error, which is okay. Then we are find number 6. We have to find the slope. The slope is the change, the gradient, this change on vertical axis. All by, give me the pencil. So the slope, we're going to the slope, which is number 6. Find the slope. The slope is the change on, that is change on the vertical axis, that is change on period squared, all over the change on the horizontal axis, which is a change on the mass axis. So we have to read off the value of t squared there, 3.5. Read the value of t squared over there, which is around 1.3. Then come down here, read out the value of our mass here, 130, and then find the coordinate of the mass here, which is going to be what again? Going to be 50. That is between 40 and 60. So we'll go to the solution. Change in t squared axis over change in m axis. 3.5 minus 1.3. Unit of the t squared or period square is second squared. That you have it there. Then for mass, 130 minus 50, unit of mass is gram. So when we subtract 3.5 minus 1.3, we have 2.2 seconds squared. 130 minus 50, we have 80 gram. Dividing this, we have 0.0275 seconds squared per gram. Then the intercept, we have to find I, the intercept on the vertical axis. The two axes started from 0, so the graph started from 0. The intercept both on the vertical axis or even the horizontal is 0. So our I is 0. The intercept on the vertical axis is 0. So we also have to evaluate K equal to 4 pi squared over S. We are told to take pi as 22/7. So substitute 4 into 22/7 squared. Then S is the slope, which we got initially as 0.02755. We put the slope down and then solve. After solving, we're getting 1,436.8 gram per second square. Inverted units, if this per gram comes up becomes gram, second goes up becomes per second. If you want to express your answer in standard SI unit, you divide 1436.8 by 1000 to convert the gram to kilogram. We now have 1.44. The gram now changes to kilogram per second squared, or the value of our K. So go to the remaining questions on that on the particular experiment. So here we are on the experiment again. Go to the remaining questions. We have done this number 7. We have done that, which we did a few minutes ago. We have done the graph plotting t squared against m. Then precautions. Number 8, precautions as usual. I made sure that I avoided polarized errors when taking reading on the meter rule. What do you mean polarized error? When you want to take reading, your eye, you have to keep your eye vertically straight on the meter rule without bending or shifting your eyes. So then number 2, I ensured I avoided 0 errors when recording the period of oscillation. That is, that had to do with the stopwatch. When you want to take reading for each experiment, you have to return the stopwatch to 0, and then before you start timing the experiment. Then number 3, I ensured that I took readings repeatedly in order to avoid random errors. Yes, one other thing is here is that when you want, the number 3 has to do with that. If you want the experiment, repeated each timing to each experiment 2 times and to the average of the time to ensure or to avoid random error. And one other thing is that when you want to say precautions in the experiment, this is a life experiment, you must use the personal pronoun I ensured, I made sure. You don't have to say you should avoid prior errors. You should or make sure errors. No, you are not using a commanding tone because you are the one that did the experiment. So you have to use the personal pronoun I, not you, not we. You did it on your own. So number 9, it says we should define Young modulus and also define force constant. Young modulus is defined as the ratio of tensile stress to the tensile strength or to the strength of an elastic material. Ratio of tensile stress to the strength on an elastic material, that is the Young modulus. While force constant, which sometimes we call stiffness, is defined as the amount of force that causes a unit extension, or it is the force ratio. Amount of force that causes a unit extension, or it is the ratio of force applied to an elastic material to its extension. That is how we define stiffness, or how we define force ratio. Okay, we can still call it elastic constant. Then number 10, we have a force of magnitude 500 Newton is applied to the free end of a spiral spring, or force constant 1.0 times 10⁻⁴ Newton per meter. calculate the energy stored in the stretch spring. So here we have force given to us 500 Newton. We also have a force constant or stiffness as 1.0 times power 4 Newton per meter. We go to the calculation. This is we are determining the values. Force 500 Newton, then the constant is 1.0 10 power 4 Newton per meter. Then we'll now look at energy. The energy stored in the spring, which is called potential energy of a spring, given by E, equal to half Ke squared, or equal to half Fe. So either we use this formula or we use this formula. But from what is given to us, we cannot apply any other formula direct because K is given to us, but we don't know the extension. So this cannot work out directly. And in this one, F is given to us, we don't even know the extension. So that becomes an issue. So either we equate the two of them, cancel extension, and then make, no. The best thing to do, or the simpler way to do it is this. We apply Hooke's law and find extension first. When you apply Hooke's law, F equal to Ke, making E the subject, E becomes F over K. The value of your F is 500 Newton. The value of your K given to you, the constant is 1.0 to the power 4, 10 to the power 4 Newton per meter. Dividing this, we are getting 0.05 meter. That's the extension we obtained from this equation. Then we can now apply half Fe. So that we can have our force is this formula. Our force is 500 and our E is 0.05. When we solve all this, we have 12.5 joules. You can still apply half Ke squared to solve the problem. You use half Ke squared, then K is already 1.0 times power 4, and E will be 0.05, then you square it. If you solve it, you still get the same answer. You can try it on your own. So, having done that, we have come to the end of this experiment on Best Science Brain YouTube channel. Always subscribe. If you have not subscribed before, you subscribe. If you are subscribed, stay connected to this channel as we offer you the best. Thank you.